Welcome to the deep dive. We're here to take a stack of your sources, articles, tech notes, you name it, and really pull out the insights you need, giving you a shortcut to getting up to speed. Our mission today is all about something fundamental to computing: memory.
Mhm.
Not the fleeting kind in your computer's RAM, but the long-term persistent kind. We're diving into file input-output I/O and also taking a look at standards like YAML that help give that data some structure.
Yeah, yeah. I mean, think about it. If a program can't remember what it did,
It's useless, right?
it's basically useless. Files are how programs hold on to that knowledge long term.
Exactly. So what are we really talking about when we say
Well, we're
files?
talking about data stored permanently on secondary storage. That could be a hard drive, a flash drive, anything that lasts when the power is off.
Okay.
And that data is just, put into named locations, the files, which live inside folders. The whole game is just getting data from that storage into your running program and then, crucially, getting it back out again safely.
And before we go any deeper, we have to establish, I think, the fundamental rule here, the one constraint that governs everything else.
Yes.
File I/O can only read and write string data.
That is the single most important concept. I can't stress that enough. Every number, every list, every complex thing you work with,
It has to become a string.
it has to be serialized, converted into a string of characters before you can save it. And then the reverse is true when you read it back. It comes in as a string, and you, the programmer, have to deserialize it. Turn it back into integers or floats or whatever you need.
So it's not optional, it's just the core of how this works.
It is the core.
Yeah.
And it all starts with one built-in function, open. That's your gateway.
Okay, open.
Right. Open gives you a file object, but the key is telling it the mode. The default is just for reading. But if you want to change things, you've got two main choices.
Sure.
Write mode, which is W, and you have to be careful with that one.
Why is that?
It just overwrites the entire file. No,
Mm.
are you sure? Prompt. Just gone.
Ah, okay. Dangerous.
Very. And then you have append mode, A, which is much safer. Just adds new data to the very end of the file. So picking your mode is your first big decision.
Okay, let's unpack that. Let's get into the mechanics of writing text data. It looks like a pretty clear three-step process. So step one, you open the file, you give it a name, and you pick that mode, either W to overwrite or A to append.
Correct.
Step two is you write the data, the actual string.
The serialized string, yeah.
And step three, this is the one that I think always trips people up when they're starting out.
Oh, absolutely.
You have to close the file. It's not saved until you do that.
It's so vital. Leaving it open can, corrupt your data, or you just lose everything you just wrote.
And what about the other way? Reading data into the program.
So that's a slightly different process, a little more involved, maybe 4 steps. Step 1 is the same. You open the file, you give it the path.
A relative or absolute path.
Either one.
Yeah.
Step 2 is where it gets interesting, reading the data itself, and we'll get into the different ways to do that. Step 3 is the real work. You use the data, you convert those strings to integers, you filter them, whatever your goal is.
And step 4, I'm guessing?
Close the file.
Close the file. It's a habit you have to build.
It's an essential habit. You're releasing that resource back to the operating system.
Okay, so you mentioned step 2. Reading the data has strategic variety. I like that phrasing. The sources here point to 3 very specific functions.
Right, and the one you choose has a huge impact on your program's speed and, more importantly, its memory usage.
So first up is read.
Yeah, read size 1. It's
Yeah.
the most general purpose one. If you give it a size like 1,000, it'll read exactly 1,000 characters.
And if you don't, if you leave it at neffish 1,
Then it tries to read the entire rest of the file into memory, all of it, until it hits that end of file marker.
okay, I can already see the potential problem there.
Exactly. Which brings us to the second function, read line. This one is often much, much safer.
How does that one work?
It's designed to read just one line. So it reads until it finds a new line character, or if it doesn't find one, it goes to the end of the file.
So you'd use that in a loop, processing line by line?
Precisely. It lets you handle massive files without, crashing your machine.
So if read is the sledgehammer and readline is the scalpel,
Good analogy.
where does the third one, readlines, fit in?
Read lines is all about convenience. It reads the whole file and instantly gives you back a list of all the lines.
So a Python list where each item is a line from the file.
Exactly. It's fantastic for small config files, things where you need to jump to line 10, then line 3, random access.
But I'm sensing a catch. That convenience must come at a cost. It sounds like readlines is basically doing what read one does, but just packaging it differently.
That's the critical distinction. You've hit it right on the head. Using read lines is super handy, but if you point it at a, say, 10 gigabyte log file,
Oh,
you've
no.
just told your computer to load all 10 gigabytes into RAM at once.
And if you don't have 10 gigs of RAM, your program is toast.
Your whole system might become unresponsive. It's why readline, inside a loop, is the professional's choice for stability when you don't know how big a file might be. You process it in manageable chunks.
That makes perfect sense. So let's talk about some practical uses. A common one would be, say, reading a file of numbers, one on each line, and getting them into a list of integers.
A perfect example. You'd open the file, you'd loop over it with readline, and inside that loop, you have to do the conversion. You'd call int on the line you just read.
After stripping off any white space, I assume.
Of course, yeah. You take the string, clean it, convert it to an integer, and then append that to your list. It's a perfect simple demo of that whole serialization, deserialization cycle.
So for people who want to practice this, where can you find big files to test the performance of read versus readline?
There's actually a great one built into most Linux and Mac systems. It's the dictionary file.
The dictionary file.
Yeah, it's usually at us_share_dict_words. It's just a text file with tens, sometimes hundreds of thousands of words, one per line. It's perfect for testing.
And for Windows users?
You might have to create one, but you could just find a large text file online, maybe an old book from Project Gutenberg or something, and save it to a path like c.tempwords.txt. The point is just to have a file big enough to feel the difference.
Okay, so you've read this huge list of words into memory. Maybe you used readlines because you know the file is, say, a couple of megabytes, which is manageable.
Right.
The sources mention a fun application, picking a random word.
It's surprisingly easy. Once you have that list of words, you just need one more tool. You import random.
Wow, the random module.
And then the function random.choice, and you pass it your word list. It instantly gives you back one random word. It's a great example of combining I/O with a standard library to do something fun, like a word game.
But this all assumes we're dealing with flat data. A list of words, a list of numbers. What happens when the data has relationships? When you need dictionaries or lists inside of dictionaries?
Exactly.
Things that need structure, but you still want a human to be able to open the file and understand it.
That is the perfect transition. Plain text files just aren't enough when you need hierarchy. And that leads us directly to data formats and specifically to YAML.
Which brings us right to our next segment. So YAML, what does that name even mean?
It's kind of a classic tech in-joke. Originally, it stood for yet another markup language.
Okay.
But it's not really a markup language like HTML, so they changed it. Now it's a recursive acronym. YAML ain't markup language.
I love those.
Yeah.
But what's its real job?
It's a human-readable data serialization standard. It's used everywhere. But its main job these days is for configuration files.
So it's like JSON.
Think of it as a cleaner, easier-to-read version of JSON. In fact, it's a superset of JSON. Any valid JSON is also valid YAML. The files usually end in .yaml or .yaml.
So readability is the goal.
Yeah.
But that usually comes with some very strict rules.
Oh, yes. And they can be a headache. The first big rule is that structure comes purely from indentation.
And here's the kicker.
No tabs allowed. You have to use spaces. If you mix them, your file is invalid. The parser will just give up.
That seems like a massive pitfall. What about something like case sensitivity?
It is strictly case sensitive. If a key is database URL with a capital D, you can't try to read it as database URL with a lowercase d. To the parser, those are two completely different things.
So that indentation and case sensitivity is what lets you build up structure, like lists inside of dictionaries.
Exactly. It's like a simplified outline. A dictionary key value pair is just key value. A list is just a series of lines that start with a dash and a space.
Can you walk me through a quick example?
Sure. Say you have a list of servers. You might have a line that's just servers. Then on the next lines, indented with spaces, you'd have address, 192.168.1.1. And then on the next line, at the same indentation level, address, 10.0.0.5.
I see. So the indentation makes that list of addresses belong to the server's key.
Precisely. And that's why the whole spaces versus tabs thing is so critical. If that spacing is inconsistent, the hierarchy just breaks down completely.
You can add comments.
You can. Anything after a hash symbol, a hashtag, is a comment, which is great for explaining what a setting does right there in the config file.
So how do we actually use this in a program? It's not built in, is it?
It's not. You need to install a package, usually PyYAML, with a tool like pip, Once you have that, you get the functions you need to read and write YAML files.
Okay, and the sources have a really great security-focused example for writing data. You use YAML.dump to write a dictionary to a file,
Right.
but it specifically mentions hashing a password before you dump it. Why is that so important?
This is such a critical real-world application. You should never, ever write a password as plain text into a config file.
Right.
So the idea is you use a library like hashlib to turn that password into a long, non-reversible string of hash.
Non-reversible is the key.
It's the entire point.
Mm-hmm.
Later, you can check if a password someone types matches the hash, but you can't go from the hash back to the original password. So if someone gets your config file, they get the hash, not the password itself. You do that step before you call YAML.dump.
Okay, so let's tie all of this together. We've gone from basic text files to this structured YAML format. How does mastering these tools translate into real power for you as a programmer?
It's absolutely foundational. The ability to control this data flow is everything. We could look at a few tasks that really show this.
Okay.
A classic one is just reversing the lines in a file. You read the whole file, maybe with this red lines, into a list, you reverse the list, and you write it back out to a new file. Simple, but it proves you've mastered the full read-write cycle.
And building on that, there's data filtering. This seems huge for things like log files. You could have a program that reads a massive file line by line using readline in a loop for safety, and it only prints out the lines that contain a specific word like error or, in the sources example, snake.
Exactly. Simple filtering like that is the gateway to all kinds of complex data analysis.
And then there's a third task that's more about formatting, not just reading and writing.
Right. This one requires some real string manipulation skill. The task is to read a file and write a new version where every line is prepended with a line number.
But not just any line number.
No, a very specific format. The first 5 characters of every line have to be a 4-digit line number, followed by a space, starting at 1. The challenge is making sure every number, whether it's 1 or 1,000, takes up the exact same width.
So you'd need to use string padding to get 1 and 10 and 100 to all line up perfectly.
Exactly. Using your own code as the input file is a great test. The output is a perfectly numbered version of your own program.
And of course, the reverse operation, taking
Right.
that numbered file and stripping the numbers back out to get the original. Being able to do both shows you have complete control.
So to just quickly recap here,
Mhm.
for persistent storage, you first have to master the basics.
Hmm.
Open, read or write, and close. And you have to be strategic about how you read.
Deciding between read, readline, and readlines based on the file size.
Correct. And then, when you need structure, you have to know when to move up from plain text to something like YAML. It's human-readable, machine-parsable.
But you have to respect its rules.
You have to. The case sensitivity, and most importantly, the absolute requirement of using spaces, not tabs, for indentation. Knowing that is the difference between a working app and hours of frustration.
Which leads us to a final thought for you to explore. We just talked about that line numbering exercise, where you inject a fixed-width 4-digit number at the start of every line. Considering how strict YAML is about indentation defining the entire data structure, what kind of unexpected, maybe even catastrophic error might happen if you tried to run that numbering program on a valid YAML configuration file? What happens when a line number accidentally creates a new level of indentation? Something for you to mull over.